start with this one.
And we can already go to. Can you scroll down on this one, or I can do it? So I think it's 10 or something, 11. Yeah, perfect.
Very classical, but also this is now the laser. So let's see if it works. Please take this before you're here.
Yeah. Perfect.
Can you hear me, Pra? Can you hear me? No? Yeah. It is on. Yeah. So we are going to start our second session of today. Also, it's second lecture by Dmitry today. The stage is yours now.
Yeah, thank you very much. So last time we talked a little bit about the basics of the zero field nuclear magnetic resonance business. And one of the things that I mentioned is that we use it to look for dark matter. And later today, we'll go back to dark matter and discuss it in some more detail. But I'd like to finish something that I meant to do last time, but our discussion was so interesting and interactive, which really the way I like it, that I didn't finish it then. So we'll finish it now. And I'm gonna briefly show you some applications now on the other extreme. So one is doing very fundamental physics, so to say, and on the other is doing some things very applied. And here it is work towards using highly polarized molecules for NMR. So let me see what I press here. Okay, sorry. That's another one of these devices I have to. Okay, good. Now I figured it out. Okay, so this is about NMR now of biologically relevant molecules, and in particular molecules that you might want to inject in a patient for some kind of diagnostics, and maybe diagnostics combined with treatment sometimes. And we want to have these molecules highly polarized. And so one of the techniques for hyperpolarization, making like really high degree of nuclear polarization, has to do with parahydrogen. So I mentioned that when you cool hydrogen molecules, they go into a singlet state, and that's a beautiful quantum mechanics effect. We can discuss it if you like later. But this corresponds to some kind of a high degree of spin order, and so we can take advantage of this. And the way it's done, you take some molecule, never mind the complicated name here, and this molecule now has a triple bond. And what you do is you do a reaction of hydrogenation. So you attach your singlet hydrogen molecule across this bond. And so now you have these hydrogens that they now find themselves in different locations on the molecule. But at first, the nuclear spin state doesn't change. It remains in the singlet state. So this is not what we want to do for some of the experiments. We actually want to have polarized C13, which, as you can see, sits here. And we're going to achieve it using the zero field NMR. So this experiment looks like this. There is here it is, this catalytic reactor. You see it here. And here this hydrogenation reaction is happening at high pressure, several atmosphere. Gas is injected here and interacts with the liquid sample. And then it's pushed into this region here inside the magnetic shield. And then there is a cycle that involves sort of rapid and adiabatic changes in the magnetic field, and that transfers your polarization to C13. And the problem with this now is that you have very highly polarized molecule that you want, but there's also a lot of junk. It's a very prosaic problem. There is a residual catalyst that you use for the reaction and some unwanted byproducts of the reaction. And so a postdoc in our group, James Eels, he brought some expertise that he gained as a graduate student at Southampton. And the technique that he proposed to use here is that what he did is he actually sort of solidified the molecule, made ice of it in a sense, so there's a solid precipitation. So then the junk can be put over there in that flask, and then he redissolves it with the aqueous solution, and now you have highly polarized molecules that are actually ready for injection into a patient, if you like. I am deliberately telling you something very down to earth here to show you the spectrum of the work that involves zero field NMR. Come on. Okay, so there is also another thing that is I find extremely fascinating, and I already mentioned the name of it. It's photochemically induced dynamic nuclear polarization, which experts don't like because it's really not anything that the words suggest it to be. But anyway, the idea is that well, if you have your appropriate sample, just by shining light, you can prepare high degree of nuclear polarization. And this is a bit similar to what you have in nitrogen vacancy centers. This is also an amazing system. Just by shining green light on diamond, you can have nearly 100% electronic polarization. And if you are doing the same thing at say around 500 Gauss of bias field, you also polarize the nuclei. So it's very easy to do. So it resembles that, even though the details are different. Here you have some kind of a spin sorting mechanism that is actually fairly complicated, but the result is that yes, like I said, you shine the light, you have polarized nuclei. And this was introduced to our group by Kirill Sheberstov, who learned this stuff during his PhD project at Novosibirsk, and then he finished it actually already in our group in Mainz. And here, what was happening was that he first performed the irradiation of the sample using light from LEDs, and this he did either at really zero field inside the magnetic shield or at earth field, and then he measured the lifetime of the polarization just by putting a gap here, and then the sample was actually shuttled into a high magnetic field for detection. And this reveals something very interesting, that it makes a very big difference in terms of what kind of nuclear polarized state you make, if you make it at real zero field or at Earth field. That makes a very big difference, for instance, in the lifetime and also in the kind of NMR signals you get. And to get an idea how this looks, so this is a magnetic shield with the cover taken off, and then there is a special illumination region with LEDs. And for the measurement here, we use something very interesting. It's actually a commercial NMR machine that is called a benchtop NMR system. As you can see, it's about this big. And then we have a robotic arm that actually can take the test tube and move it between the spectrometer and the zero field region. So it's kind of a fully automated operation. I should say maybe a word here. It's interesting that these machines, this is a high field NMR machine. It operates at a field of about 1.5 to 2 Tesla, something like this typically. And they appeared only a few years ago, and they were enabled by the advent of special magnets that are called Halbach arrays that can have reasonably high field and also very homogeneous field. Because before that, the permanent magnets didn't really have sufficient homogeneity to do real professional NMR, and now they have. And I want to say that the person who developed magnets for this purpose as part, I guess, of his postdoc, I think, or maybe PhD, I don't know, Peter Blumler, he's actually affiliated with our group now as well. So yeah, okay. So there are these results that were published recently, and this is Kirill Sheberstov. Like I said, his PhD work started in Novosibirsk, and so he brought this Novosibirsk collaboration. His advisor was a wonderful scientist, Konstantin Ivanov, who unfortunately did not see this paper come out. He fell victim to COVID. The results of this paper is that we demonstrate significant enhancement of NMR signals. There is evidence. You see, normally when you work with NMR at a finite field, nuclei have different magnetic moments, and so you cannot, for example, form singlets out of molecules that have different gyromagnetic ratio, because they precess at very different frequencies. If you go to zero field, that's fine. You can. I showed you in the beginning that we actually work with a singlet and triplet state formed out of hydrogen and carbon. And so here, this work shows that if you form the singlet state, it is kind of stable towards various perturbations and can live a long time. That's long-lived heteronuclear singlets. That's a very interesting thing. There's a lot of interest to this kind of systems because, for instance, if you want to do imaging of the brain and you want to inject some polarized stuff, usually it takes quite a while for the molecules to reach the places you want to image, and the decay of polarization is faster than that, so it's a problem. So if you can have some kind of long-lived polarized state that you can then convert, singlet you can't observe directly, right? But if you can convert it then in something you can observe in nuclear magnetic resonance, this is a interesting possibility of doing this kind of imaging. Okay, and where's the sound? It's supposed to be with sound, but this is another experiment. Here, actually, it's inverse. Here, the polarization is happening at Earth field, as you can see now. And so the robot first takes the sample, then the LEDs start shining, and then it drops it down here, and we detect at zero field. So if we do a control experiment and don't apply the light, nothing happens. But if we do apply the light, we see nice signal. So now we can have all kinds of combinations involving zero field or small field. So we can polarize and detect, and the physics is extremely rich. But we feel we're very excited about this. We feel that there will be a lot of interesting applications of this coming up. So this is Piotr Put, who is maybe Piotr. Are you here? There he is. We can hardly recognize him in a mask, but there he is. Piotr is one of the students in this ZULF NMR, and Anjusha, also another one there. Yes, it's a wonderful group of people, and as part of that innovation training network, the students also had to do secondments and travel to other labs, and Piotr traveled to Berkeley to work with Danila Barsky, and Danila Barsky currently he moved from Berkeley now to Mainz. He was already my dear collaborator at Berkeley, but now he's a junior group leader as part of our group. Here she is a Sofia Kovalevskaya fellow, and there is a Humboldt Alexander von Humboldt Foundation, and it gives 1 or 0 depending on the year awards in a particular field, and Danila impressed them with his proposal in chemical engineering based on ZULF-NMR, that they gave him this fellowship, and so he's now with us there. But this machine was put together actually by Piotr at Berkeley, and you can see that it is it fits on a cart and has all the elements there. There's your Halbach magnet and shield and everything, and this works very, very well. There are some elements there. Maybe I don't need to go into great detail. I believe these pictures were made by Piotr. And so this was published in a paper that is significant because here it is about doing real spectroscopy in a very simple device on biologically relevant molecules. And so here you see a few of them. So this one is glycine. It has very sharp lines, and this one has a bit of an ugly spectrum because this molecule is complicated. But you would notice that this is actually glucose, so it's a very, very important molecule to measure in the body. Okay, so here's another example along similar lines, and this is again a work in collaboration with friends in Novosibirsk. There's a different collaborators. This is Professor Igor Koptyuk, and this is Dr. Kovtunov. Unfortunately, also we lost him to another disease. But anyway, it's very dangerous to collaborate with my group, I'm afraid. Yeah. It's more sad than funny, but okay. And this is Dudari Burueva. She was a graduate student who visited us to do this project, and now she's a postdoc, and we're excitedly awaiting her second visit later this year. And here there are a couple of things that I'd like to point your attention to. So I mentioned already that because we work with very low frequencies, we can actually look inside metal containers. Okay, it's maybe not very fundamental, but for practical purposes, very important. And the other thing is, so you can do sort of static measurements, but in when you're studying, for instance, catalysis, you want to see the dynamics of a reaction. And so here we demonstrate a measurement inside a metal container, by the way, using a commercial magnetometer here, and also monitoring of chemical reaction. So here it's kind of similar chemistry to what I show you with maleate. So we start with a precursor, and then we have a reaction here, and this now is happening in a zero field. The catalyst is mixed in the solution. It's a rhodium-based catalyst, a typical thing that you have, and then you see this is a triple bond, so you can attach two hydrogen, and then you can do it again, and then you end up with this dimethyl succinate molecule that only has a single bond. So you have now an initial molecule, then an intermediate product, and then a final product. And if you look now, this is a color-coded picture of the spectrum. So this is the experiment, and this is interpretation, where these lines are attributed to malate, and these ones to succinate. And then you can actually plot how this depends. Oops, excuse me. How this depends on time, and so you can see that this intermediate product appears and then disappears as the reaction goes on, and then the final product appears, and then the nuclear relaxation happens, so the signal starts to go down. So it's really monitoring catalytic reaction inside metal. So this is kind of exciting, and this is angewandte chemie. Angewandte means applied. It's one of the important journals in chemistry, and they were convinced this is interesting enough to publish.
Sorry, just a stupid question. What kind of signal you get to see to monitor the reaction?
It's a zero field NMR. It's the NMR signals like those shown over there. So you see some lines, you see some lines at first are absent, then as the intermediate polarized product appears, they appear in the spectrum, and then they decay, and the final product appears and then also decays. So that's the dynamics that you see here. Exactly. Yeah, that's this could be maybe a minute for the whole thing, something like this. Yeah. So not super fast. Yeah. All right. So now actually I would need to confess to you that almost all my life I was trying to stay away from the topic of quantum computing. Why? Not because it's not interesting. I think it's very interesting, but because I think there are so many smart people working in quantum computing, and people with a lot of resources. So I said, let them, we'll do our thing. We will lose the competition, you know, to everybody if we go where everybody else is going. But my colleague, Xinhua Peng, she's a professor at the University of Science and Technology. She convinced me one time that there is something we could do, and her argument was that she had to come to Berkeley and go on a long bike ride with me to yeah. Okay. So the idea was that you know, NMR quantum computing is maybe not the most popular platform, but yet it's very interesting, and there was a lot of basic quantum computing science that was done with NMR, and the distinction between what is really quantum computing and what quasi-quantum computing was established there. And what Xinhua said, she said, look, in ZULF, we have a completely different regime, unusual regime for NMR. So it's worth at least to take a look and see what's going on. And so that looked like a quick experiment. That's you know, it's a usual trap. Yeah, it took several years for us to do it in the end, and we couldn't even complete it at Berkeley, so we had to finish it at Mainz. But then it worked, and the idea here is that we actually demonstrate a complete set of quantum two qubit quantum gates, with one qubit being the proton and another qubit, another qubit being the C13. And with pretty high fidelity, actually. So, and this is important because this is like a prerequisite for efficient quantum control and quantum computing, if you want. The tricky thing is that if you have two qubits, you need to be able to address them separately, okay? But if you work at zero field, it is tricky because what do? You apply a magnetic field, your spin starts rotating. But not only proton, but also carbon rotates, okay? So it's you can't really selectively address them at zero field. So the trick that is played here is that you notice that there is a particular ratio between the gyromagnetic ratios between carbon 13 and the proton, and the proton has a very big gyromagnetic ratio. So if you take say carbon 13 and you do the ratio is about 4. So if you do let's say a pi pulse on carbons, you have a 4 pi pulse on protons. So now you can play some games, and it's not exactly, there's I forgot, 1% difference or something, and you can compensate it with this imperfection with a proper pulse choice of pulse sequence, and so in the end you can do it. There are other ways. A more prosaic way of selectively addressing carbons and protons is to temporarily apply high field, which for us would mean, you know, something like Earth field, and then you already can selectively address the two spins with micros. Sorry? Yeah. This one? Yeah. Yeah, there's a sum. Yeah. Okay. So this was done. This work was done by Xinhua Peng, the professor at USTC, and this is Min Jiang, who is known more by his name Billion, who spent a lot of time with us at Berkeley and also at Mainz, and now he's an assistant professor also at USTC. Yes. Yeah. Yeah. And this is Teng Wu, who was a postdoc at Mainz, and now he's an assistant professor at the Peking University in China. And John Blanchard was a graduate student with Alex Pines at Berkeley, but collaborating with me a lot. And then he was for a few years a postdoc with us at Mainz, and now he's, I think, what is it called, director of NMR of a company called Envision, which is based in Ulm. Yes, Andrusha. Yeah. Yeah, so okay, so there it's a bit involved, and maybe I don't want to go into many details here, but you can actually play tricks with this, so to in fact selectively affect either. Well, I gave one example. So if you do, if say you want to do a pi pulse on a proton, you do it, then the carbon does a 4 pi. 4 pi is okay. Yeah, yeah, there are some ideas about how to do this, but again, I'm not really in this business, but yeah, there are some ideas. Definitely, there are molecules with more spins that you can do. So scaling, I would say, to 6 is not a problem. Scaling to 1,000, we need something else. Yeah, but may not be impossible. But some, well, I mean, to me, the purpose of this is just to maybe draw attention of the professionals that there is exists this kind of. Then you might say, okay, why go into trouble of doing this at zero field? And we give some examples of Hamiltonians that you can simulate, for example, for quantum simulation, that are very hard to make in high field NMR, but you can do here. So maybe, I don't know. Any more questions? Okay. So this, I guess, I already mentioned. There are, I heard a few people in the audience doing NMR, of course, and with the nitrogen vacancy centers. And Jusha, of course, is a big expert. So I just want to repeat again that one attractive possibility is to combine all the weird things, all the extreme properties in one, and so measure a single molecule using a single spin sensor, and also do it all at zero field. Okay, so that's that hasn't been achieved yet, but we're actually collaborating with Anjusha and Fedor and others moving in that direction. Yeah, I believe that I showed you this in the beginning. So the sort of the basic thing about the ZULF NMR concept is that you have a look at the 3 stages of the NMR experiment. So you need to polarize the nuclei. You need to do encoding. Now, encoding, there are within nuclear magnetic resonance, there are 2 big branches. So encoding is that you somehow, why do you do this experiment? Is you want to learn something about the system. And there are 2 main things that, 2 main branches. One is that you know what kind of spins these are, say protons, and you want to know where they are. And this is imaging. Yeah, you want to know what the location of those spins. And another big branch is spectroscopy. So you have your bottle or test tube, depending on your imagination. We do actually experiments with alcoholic beverages nowadays for not NMR experiments. I mean, so you also need magnetic field or magnetic field gradient for encoding, and here we have to think how to replace that magnetic field. So in the case of spectroscopy, I hope I have convinced you already that this J coupling interaction, the residual dipole-dipole interaction, can be a very nice fingerprint there. And then for detection, of course, we rely on these non-Faraday induction methods, and this enables a zero field experiment. So in the end, you can have an NMR experiment completely without magnets, and this was an earlier paper where we actually demonstrated this, and I really like the artist picture here, because it actually it looks at first like abstract art, but in fact everything here has its meaning. So you have this molecule to which parahydrogen attaches, okay, and then there is evolution, and the polarization, the spin order spreads over the molecule. And while this is happening, there is an atomic magnetometer that consists of a small vapor cell with a pump and probe light, interrogating it, and in the end you record the spectrum. And for this particular molecule, it's a system where you have a group of line at J and 2J. So these are sort of the basic lines, and then they are split by interaction with other molecules, other atoms in the molecule. So you have this substructure. So this is an extremely informative picture, actually telling you all about the experiment. Okay, then we talked about this kidney, chemically induced dynamic nuclear polarization. We mentioned NV centers here as interesting players that may enable extreme NMR, and we talked about monitoring chemical reaction inside a metal container, and we started our discussion with actually talking about how to use zero field NMR to look for dark matter, and this is the dark side where we're gonna go next after we see if you guys have any questions.
I have a very basic question that maybe I missed. Like, which kind of molecules are used for this protocol? Because we have very complex molecules.
Then the spectrum gets very complex. We are trying to learn. We're trying to learn how to deal with big complex molecules, and there are some ideas. So, for instance, if you use hyperpolarization, you can try to polarize just the parts of the molecule that you want to look at. Those will simplify the spectrum. There are also techniques of optimal control where you apply certain pulse sequences so you can drive the polarization either to particular groups that you want to look at selectively, or maybe particular locations in the molecule, and this is developing. So this field is no longer like in its infancy, but it's still a toddler. So I think in the future, I'm very hopeful it will develop into degrees of sophistication comparable to high field NMR. And I think, and you know, judging by going to big NMR meetings, for example, that there are actually more people probably working in NMR than in the whole other, which is part of chemistry now, than all of physics, I think, because it's very important for medicine. Yeah, so you cool the gas to low temperatures, and even if you just cool it to liquid nitrogen, you can already have like 50%, and if you go towards liquid helium, you basically have 100%. And that's all you need to do is cool it. The problem is that the para-orta conversion is very, very long. It could take weeks, a couple of weeks. So you don't want to do this. So you add what is graciously called a catalyst to do this, but it's actually rust. It's that's what it is. And the idea is that, you know, the spin singlet is very stable. So if you have any kind of perturbation, it affects both spins the same way. So the idea for this conversion acceleration is that your molecule comes to a place where there's very strong gradient of magnetic field, strong even on the size of the angstrom size of the molecule, and would flip one spin more than another, and then there, you know, basically the distribution between singlet and triplet will be statistical, and the statistics says that it has to be parahydrogen. That's all. Yeah, no. I mean, you have to be careful about materials and so on, but Anjusha, please speak up. I can't hear. Yeah, in fact, when we started, we first did more of the imaging experiments than spectroscopy, and you can look inside porous metals, and we studied the diffusion of liquids inside the porous metal, for example, and recently Michael Tyler has done similar things at the ICFO. Yeah, this is one of the ongoing directions, is to learn to do this. There's a problem in NMR known concomitant gradients, that if you know Maxwell's equations, you know, they get on your nerves, right? You apply the gradient in one direction, and there appear other concomitant gradients, and you need to deal with them. And there are ways to do this. Okay, so we have plenty of time, right? Okay, so let us switch the presentation. I think this is it. Yes. Sorry, I forgot to show you. So this is our lab. Various people who did the work that I presented. So this is Danila Barsky. So we have, as I mentioned, close collaborators in Novosibirsk, and so Piotrek is here, and his advisor is Professor Pustelny, and I'm very proud. I was his PhD co-advisor together with Professor Gaulik. So yeah. So anyway, this is our team, and all right. So I prepared a special version of this talk for this school, and copied it on my stick, and it destroyed itself. So just before this, we had to find another presentation that I prepared recently for for another school, but luckily that was not so long ago, so most of the information is the same here. And so now we're gonna talk about ultralight dark sector, and here are some important players in this field. So actually, for Professor Schnabel, I want to show that this is Pierre Sikivi, Professor Pierre Sikivi. He's convinced that dark matter in our galaxy is a Bose-Einstein condensate, and so he's your man. Yes, but the other people are also very important. Well, this is Marie Curie, unfortunately not quite alive. It's in Korea. This was one of the last live meetings before the pandemic. Okay, I think it was like November 2019. Yeah, and this is Bela Majorowicz and Axel Lindner. They are very active experimental physicists searching for axions. We'll revisit the axions. And this is Ariel Zhitnitsky. He's a theorist, also one of the classics of the axion theory. And so this guy is convinced that dark matter is BEC. This guy is convinced that dark matter is axion quark nuggets. The pieces, if I have time, I'll explain what it is, but these are basically macroscopic, 10 to minus 5 centimeter pieces of the baryonic matter from the early universe. And in contrast to most other dark matter that interacts very weakly, allegedly, with our normal matter, this thing, when it hits the Earth, it deposits the energy on the order of a small nuclear bomb. And still, we may not notice it because it's not localized. It makes like a line. It goes through the Earth and annihilates as it goes. And so this energy deposition is in in a string. So and we try to look for it with actually gravimeters and seismometers and whatnot. So anyway, these are important dark sector folks. So I think it's a very interesting time to do physics, actually, because I think nobody will tell you that the world is understood. That would be really wrong thing to say, especially now. And this misunderstanding is so gross that I don't know, it's bigger than an elephant in the room. For instance, we are being told, okay, and you can trust it or not, that most of the matter in the universe is some mysterious thing that we don't know what it is, okay? And big problem, but not the only one. There's an interesting problem which we should be thankful for having, and this is the fundamental properties of matter and antimatter are quite symmetric. So nobody has seen a difference yet. Well, of course, say you have an electron and it's negatively charged and the positron is positively charged. There is this difference, but nobody has been able, for instance, to measure a difference of magnetic moment between electron and positron. So there is this symmetry. And then the question is, why is that everything is matter and there is no antimatter? Very little. You know, when Dan Brown had to write his book about antimatter, he had to place it at CERN because you make antimatter, you know, there are very few antimatter particles come to us, you know, in the form of cosmic rays, but basically all universe is made out of matter, apart from dark matter, of course. So why? Where's the antimatter? If they're so symmetric, where is it? It's good that there is this asymmetry, because if we had the same amount of matter and antimatter, we would all be light, you know, and we'll be like school of photons or something like this, you know, no chairs, no tables. So we don't really understand that. Then there are some other things. So if we believe the dark matter hypothesis, there's about the same amount of dark matter and normal matter, maybe 5 times more dark matter, but it's on the logarithmic scales. Why is that? Why is not 10 to the 9 difference? Okay, so maybe it needs to be explained. Then there are other subtle things. You know that there are different interactions: electromagnetic, gravitational, weak, strong. So there, the theory of strong interactions is called quantum chromodynamics, and it is very easy in the framework of chromodynamics to introduce combined violation of charge symmetry and spatial inversion symmetry. And when we do experiments, we don't find that, and that is called the strong CP problem. Another mystery. And okay, yet another mystery. So we used to, you know, most of the constants, numerical constants are on the order of 1 or pi or 2 or something like this. So everything usually you very rarely you have some huge numbers appearing. And then we have learned that there are these important scales in physics, like the grand unification scale, where the strengths of all interactions is becoming similar, and then the Planck scale, where quantum gravitation basically becomes quantized, and those scales are in the GeV units, 10 to the 16, 10 to the 19 GeV, very high, and all the particles are very light. All the particles where we know they are maybe half an MeV or less than eV for neutrinos, or maybe GeV like a problem, but not 10 to the 19 GeV. Why is there such a hierarchy? What gives this? That also needs to be explained. Then we won't even mention that there is a potentially an even bigger problem of dark energy that makes the universe accelerate faster and faster. So there are all these problems that we have now, and we need to solve them, and probably we'll solve them soon because they're so egregious. And one intellectually appealing approach to this or scheme is that maybe actually these are not different elephants. Maybe there exists some kind of a simple explanation where all these puzzles will be explained by one. And there are some good candidates. So we're going to talk about this axion, for example, and it's a nice ingredient that can potentially solve a lot of these problems, and that's probably a good thing. Anyway, let us now focus a bit more on the dark matter problem. Where is it coming from? Well, it's many decades back. Astronomers were looking in the sky and measuring speeds of objects, and there was this guy you may have heard of, Fritz Zwicky, and he was actually looking at the speed of galaxies in a galactic cluster, and he found that he can't actually explain what he's seeing. The things were moving way too fast for the mass that he was seeing. Well, but it's, you know, astronomy. You can't go there, see what's going on. You can only look in the telescope. So it was a problem, but not really like worrying people that much. But in the 1970s, astronomers started looking at what's happening with stars rotating in the galaxy, in the Milky Way, in our own galaxy as an example, and maybe other galaxies as well. And one of the famous people doing this was Vera Rubin, an astronomer who did a lot of work. And as a result of her studies, the problem became really acute. So it's a rotation curve problem. So, and when I was a schoolboy in Novosibirsk, I studied in Novosibirsk. My first physics class was in 6th grade, and so we studied the motion of planets there. So I call this effect a bit of a sixth grade physics, right? And the question is, suppose that you have some object, some mass, and let's think about the center of the galaxy, okay? And okay, so we can have some stuff here. We're not gonna look at you know, the details of distribution there. We're just gonna go to the periphery of the galaxy, and then we can say that this is all effectively sitting in the center, and we will calculate, for simplicity, circular orbit of some star, and what we find, you know, what we need to write, it's really 6th grade physics. So mv square over r, this is the centripetal acceleration, and then we have to write m like this. This is the mass of the center, and this is the mass of the star. That is cancel, and you divide it by r squared. So you can see that v should scale like 1 over square root of r. See, one line for 6th graders. So if you plot now the distance, and here you plot v, so you I don't know, let's not worry about this fuzzy part in the center, doesn't matter. But then we predict that it should go like 1 over root r. And for all the galaxies that we observe, for all the galaxies, this looks like this. It instead of dropping, it goes to a constant. And it's a different constant for different galaxies, but That's the observation. What the hell is going on? And in order to explain this, you can actually you actually need to assume a certain distribution of some matter here that you are not seeing. So that's the rotation curve problem, and it is, like I said, 1970s, 1980s when this became an acute problem. All right, so dark matter was one of the first things that was proposed, that actually we're not seeing some of the matter. That's the easiest thing to think. But that was not the only thing. The other thing that was proposed actually by a professor at the Weizmann Institute, his name is Mordechai Milgrom. He's still alive and well. And thanks God, I spoke with him this very recently, and he noticed something really interesting. So we use Newton's laws, right? So how do we know the laws of gravitation? We can nowadays measure gravitation in the lab, but it's a big problem that the gravity is so weak that it's hard to measure precisely. If we go to large scales, also it's very difficult and it's very problematic with this, as we can see. So all our knowledge of gravity basically comes from astronomy, from how planets move around stars. That's what we, and then we project it all the way to the size of the universe. So what Milgram said, guys, let's slow down here. Maybe let's be humble. Maybe we don't understand how gravity works on larger distances. And he proposed, in fact, this beautiful framework that is called modified Newtonian dynamics, or MOND. And despite of what you might hear people say, this is not dead. This is alive and well. The challenge that this idea, which is very appealing in my opinion, immediately faces is that nowadays these rotation curves is only one piece of evidence for dark matter. There is actually a whole bunch. So and this piece of evidence, it comes from different scales. So the smallest scale is galaxy. The next one, as I mentioned already, the clusters of galaxies. Then there is gravitational lensing, and there is theories of formation of the structure universe, and all the way to cosmic microwave background. So it's all the way from the size of the universe down to the size of galaxy. And so you need to come up with a modification that actually works on all scales. And it's a bit hard because, for instance, there is gravity is supposed to be like 1/r potential, right? And physicists always like to do Yukawa potential, where they say, okay, it's 1/r, but there is an exponential cutoff with some scale. But that doesn't really work this way, because you would need to figure out how to do this differently on different scales. But anyway, the people working on dark matter are very much opposed to this alternative idea. But my personal opinion that before we find non-gravitational evidence for dark matter, we should really keep our minds really open to various possibilities. Yes.
Is it like competing with general relativity?
It would be general relativity in this sense would be sort of Newtonian in a way. So there is nowadays there is Armond, which is relativistic version of that. It's some extension of this. Some extension. Yeah. Okay. Now I was also involved recently in a completely different exercise, and this was really, I should tell you this story because I was a student more than 35 years ago, and so there's one of my professors at the university who taught me condensed matter physics and so on. I kept in touch with him, and I invited him to come. He recently retired, and I invited him to come and spend some time with us at Mainz. And he said, "Sure, let's do this, but let's find a problem to work on when I'm there, which is of common interest." And this dark matter turned out to be one. And this gentleman, his name is Professor Ryutov. He is an expert in plasma physics, completely different thing. But he noticed something interesting. So imagine that a photon, which we assume to have zero mass, has some small mass. It can have large mass, but it can have small mass. Then you actually have to rewrite your Maxwell's equations because, for instance, the photon field doesn't have to be transverse anymore and things like that. And it turns out that this was done many years ago by a physicist named Proca, and you can write a very nice equation system called Maxwell-Proca equations, and you can find it in textbooks. If you take Jackson's classical electrodynamics, there's a chapter on Proca electrodynamics. And because the physics of plasma depends very strongly on the Maxwell's equation, that's what it is plasma physics, basically solving how charged particles move in electromagnetic fields. So what Ryutov noticed is that you can actually put limit on mass of the photon by looking at the measurements obtained by spacecraft in our solar system. And so all the particle properties are collected by particle data group. You can go online and look at pdg.org, and you can find all the masses and magnetic modes and whatnot of all particles, and also limits on sort of exotic physics. And the limit on the photon mass listed by particle data group was determined by Professor Ryutov from these solar system observations. So his idea was, let us look at what a small mass of a photon. By the way, the current limit is 10 to minus 18 electron volt for the photon mass. And he wanted to look at even smaller masses, but how would it affect what's happening in the galaxy? And the galaxy is full of ionized gas, and there are these stars that form and then explode and so on. And so there is exchange that's going on in the galaxy, and you can then try to see with these Maxwell-Proca equations what was happening. And when we started working on this, we got super excited because we found that 10 to minus 5 of the present limit of the photon mass explains is enough to explain the forces needed to reproduce these rotation curves. But now I must say how science should work, right? So you have some theory, but then you have to see it through. You have to see what kind of predictions it makes. So after initial excitement, we said, well, there are not only these giant big stars that live for a short time before they actually rotate around the galaxy, they form and get destroyed, but there are old stars like our sun. What should happen with them? And so our logic here predicted that they decouple from the plasma very early and should all be moving on orbits that are highly elliptical, and they don't. So that unfortunately the logic of this exercise cooled down our enthusiasm. Well, nevertheless, we think it was a fun thing to do. Okay, so some people still think that it's something more or less ordinary that we for some reason are not seeing, although this is very subjective, and science shouldn't be decided on the basis of popular opinion. But what I hear from people working on this, that the room for any of that is shrinking. But before we really find the dark matter, nothing is really dead. It can be resurrected. Now, sort of the most popular idea for what dark matter could be is something that's called weakly interacting massive particles. And the idea is very simple, that there is some particle with sort of a normal mass comparable to the mass of a proton, or maybe 100 times heavier or something like this. So it's in the GeV range. And it so happens that it interacts very weakly with normal matter and light. And so we just don't see it, but it's there. And it turns out that it's very easy from the point of view of particle physics to think of what these WIMPs could be, and they fit so nicely into the picture in the standard model, sort of how we think of particle physics, that people have been talking about this WIMP miracle. So how well they fit. The only problem with these guys is that after 40 years of search, nobody can find them. The window is not fully closed yet. There's still a possibility that WIMPs exist, but not finding them made people sort of look at some other possibilities. And I guess the next important class of possible dark matter particles are ultralight bosonic particles. And we will discuss why, if they are ultralight, they have to be bosonic, maybe in the beginning of the next hour. And they come in different varieties based on their spin and internal parity. So for instance, axions that we mentioned many times are spin 0 particles with odd intrinsic parity. And the special thing about axions is that they solve the strong CP problem. Okay, so they will kill at least 2 birds or be 2 elephants at the same time if you want. Then there is a more general kind of class of hypothetical particles. These are ALPS axion-like particles, so they are very much like axions, except they don't solve the strong CP problem. Then there are scalar particles called dilatons, and so this intrinsic parity turns out changes completely the way this particle interacts, and correspondingly the way we would want to search for them. And be prepared. I'll show you really bizarre ways to look for these guys. Then there are vector particles, spin 1 particles, like a photon is a spin 1 particle. So these are typically called dark photons or hidden photons or something. And then there could be higher spin particles, but people don't really talk about these very much because the theory gets complicated and not for any other particular reason. And then there is this whole different paradigm of axion quark nuggets or anti-quark nuggets, and we have time, I'll tell you about them. Okay, so now I need to tell you another story. So I was educated, so my undergraduate work and then PhD was in atomic spectroscopy, tabletop atomic spectroscopy. That's my background. And some years back, now already 8 or something, I kind of started doing this dark matter work. And so in the beginning, as a newcomer, I had to learn the basics about this. And as I was doing this, something really struck me. One very simple thought really struck me. On the one hand, we know very little about the nature of dark matter. On the other hand, once we set our mind that this is some kind of a paradigm, in this case it would be bosonic particles, then we can deduce almost from nothing, from very little information, we can deduce amazing things. So for instance, we can deduce the spin of the dark matter particle. How on earth can you deduce? I'll show you in a second. It's all on this slide. Let's start on that. So from the rotation curve measurements, we can work out what the density of dark matter has to be in the galaxy, and this is about 0.4 GeV per cubic centimeter. 0.4 GeV per cubic centimeter. So it's, if you want to think about it, is you take 3 cubic centimeters in the galaxy, and it will have 1 proton mass equivalent in this. And you might say this is very little because this has 10 to the 23 per cubic centimeter, right? And not on the order of 1. But the galaxy is so big and fluffy that if you do the numbers, this is in fact the majority of mass by a factor of 5. And this sort of is an experimental input. Okay, so now the next thing is, and I'm not going to do experiments on humans, but I'm going to do an experiment on a laser pointer. So if I take my laser or your laser pointer and I toss it, okay, it comes back. And if I toss it harder, it comes back. But if I toss it faster than escape velocity, which is a few kilometers per second, it's not going to come back, it's going to fly away. Yeah? So galaxy is also a gravitating object, and you can calculate the escape velocity for the galaxy. And this calculation leads to this value being about 10 to minus 3 of the speed of light. Now, these observations tell us if there is dark matter, which is responsible, it is kind of associated with the galaxy, it doesn't fly away. So now we make our first conclusion, is that just from a confinement to the galaxy, this is non-relativistic system, okay? So we don't need to worry about complicated relativistic equations. We just can use non-relativistic mechanics to describe it. It's called cold dark matter. So far it's like 6th grade. Now for the next step, we have to go to the first year of graduate school. And in the first year of graduate school, we learn quantum statistics, that there are bosons and fermions. And we learn that fermions, they don't like any two identical fermions cannot have all the quantum numbers the same. And so, for instance, if you want to put them in the same box and at low temperature, the only way they cannot find themselves when their wave functions start to overlap, not to be in the same quantum state if they start moving rapidly. And this is the Fermi distribution, right? It's it's a velocity goes up and up as the more of the fermions you put, and then there is a Fermi velocity. That's a cutoff. So now let us assume the simplest thing. Of course, we don't know what dark matter is, and maybe it's something complicated. Maybe it's elephants made of dark matter flying around, as you will see later in my slides. But the simplest thing is just one type of dark matter particle. Then, if it's one, let's assume some mass. Then the density of these particles, the number density, is the energy density here, the mass density divided by the mass of one particle. So you immediately calculate how many of those you have. And then you do this calculation for the Fermi velocity. Now you have all the numbers. And once again, your Fermi velocity better be smaller than the escape velocity from the galaxy. Otherwise, dark matter is gone from your galaxy. Yeah? And so it turns out that it's about 10 or 20 or something like that. Electron volt is the cutoff. So if your dark matter particle is lighter than 10 electron volt, it better have an integer spin. So this is how we say something about the spin of the particle from nothing. It's amazing. We can continue this. So I already talked about this last time, that when you have a whole bunch of bosons, then maybe it's not so good to talk about individual particles. Maybe it's better to talk about the collective field, just like we do for electromagnetic field oftentimes. I mentioned that the Q factor of such oscillator is 10 to the 6. So now watch closely the magic on the board, where it comes from. It's interesting. So the field should oscillate at a frequency given by the total energy of the particle, and the total energy is the rest energy, mc squared, plus non-relativistic physics, mv squared over 2. But v should be less or on the order of 10 to minus 3 c. And you square this, this is your 10 to minus 6. That's all there is. See? Not very sophisticated. So this gives you the Q factor for the oscillator. Now, Pierre Sikivi, who thinks this is Bose-Einstein condensate, will tell you that it's actually a much bigger Q factor. Maybe, but it cannot be smaller, because otherwise this term will be too high and the molecules will fly away. All right. Then there is another funny thing you can say, which is the particle cannot be less than 10 to minus 22 electron volt. Why? Same reason. Has to be confined to the galaxy. If it's 10 to minus 22 electron volt, the de Broglie wavelength is equal to the size of the galaxy. So if it's lighter, it has to be bigger. Nah, it has to be the size of the galaxy, no bigger than that. So this gives you sort of the lower limit for what it can be. And so in the moral of the story here is, once you sort of set your mind on a track of what this is, you can make a lot of far-reaching conclusions. And by the way, a lot of people think of different. This is like a burning problem. We had this discussion with my colleagues over dinners and lunches in the last days. So you can come up with many ideas for what can it be, but because of the situation that you kind of need to make it consistent with what you are seeing, restricts sort of what kind of models you can have. Okay, so I think it's maybe a good place to pause. In the next part, I'll tell you some really weird ways to look for these things. Thank you.
So maybe we can have a couple of questions. No? Yeah. Maybe we can have a couple of questions now. Okay, maybe people can discuss with you during lunch break also. And we will be back with you again after the lunch break.
We start at 1:30?
Yeah.
Just wait a second. I want to do a little advertisement for the lab tours tomorrow. We will have the list ready for you during the lunch break, so you can register there. You can. There will be three main spots where you can go. One is IST in Klosterneuburg, the other is University of Vienna, and the other one is just you can visit the labs here. So for just let me show you some nice pictures of IST to motivate you to go where RIA works. It's in Klosterneuburg. They are very rich, as you see, in 2020. They absorbed 25 million euros. And they are growing quite fast. Like it's established in 2009, if I'm not mistaken, and they already have 59 professors, 250 PhD students, and
so divide this to 25 million by 250 PhD students. Yeah?
rather by 60 professors.
Professors.
Yeah, so there you can visit Fink's group, Professor Fink's group, where Ria works, or Honor Hoston's group, where Sebastian is working there, or Lemeshko group. We had, I think, Misha, who was working. Is he here today or not? Who is working there? So integrated devices, quantum sensing, and condensed matter physics. At the University of Vienna, you can visit Markus Arndt's lab. Both Stefan Kuhn and Christian Knobloch, who worked in these companies, graduated there. You see this single molecule kind of interference, like the molecule interference. That top there is from Philip Walter's lab. It's a 10 micrometer lens and levitated superconducting stuff in Markus Aspelmeier group. So quite interesting. And here you can visit our cold atoms lab, the experiment that Benedict gave a talk about, and Philip Haslinger's group. So register there. The other thing I wanted to mention is you can get your certificates from the registration desk today. There you can get, if you presented a poster or a talk, you can get a certificate, and your payment certificate you can also get there. And today we will have the VCQ special lecture by Professor Schnabel. And after that we will have snacks and wine. And yes, the lecture will be here in this very same lecture room. Questions? There will be a list now. There will be a list prepared now in the registration desk. So just register today, put your name there in one of the 3 papers that are there, and then you'll be fine. Great, thanks. Enjoy your lunch.